Okay, so this problem we have the series from k equals 0 to infinity, negative 1 to the k divided by 3k plus 5 to the fifth. It says evaluate the partial sum for n equals 2, and then find the upper bound for the error, which is the sum, the true sum if we go to infinity, minus the sum, partial sum if we only use n equals 2. Okay, and what this says is if we can put it in this form, and it's a convergent alternating series with non-increasing magnitude, then the remainder is this, and you can approximate it by saying that the remainder is less than the next term after your partial sum. Okay, so if we can get it in this form right here, change it to this form. It doesn't have to be a k, but it has to be of this form. Okay, then if you find the term right after your nth partial sum, it'll give you the error. So what we want to do first is find the partial sum with n equals 2, and then we want to find the third sum, and that will give us our error. Okay, so my first step is to try to get this to look like this. Okay, so there's a couple little changes I need to make. So if I have a series, let me write this down, k equals 0 to infinity, negative 1 to the k, divided by 3k plus 5 to the fifth. Okay, I want to get it where it's k equals 1. I want to start at k equals 1. Only I'm going to use n. So I'm going to substitute in k is equal to n minus 1. So everywhere I see a k, I'm going to put an n minus 1. Okay, so let's do that. So here we have the series from n minus 1 equals 0 to infinity, negative 1 to the n minus 1, times 1 over 3 times n minus 1 plus 5 to the fifth. Okay, and I'm going to clean that up, and I'm also going to change this. The formula had an n plus 1 here, which is fine. We can just change this to an n plus 1. The reason for that being, I'll put this over to the side over here. If I have negative 1 to the n minus 1, that's the same thing as negative 1 to the n plus 1 times negative 1 to the negative 2. Now think about that for a second. Make sure you understand that. So if I combine, they have the same basis. So if I combine these, n plus 1 minus 2 gives me n minus 1. So these two things are equal. The reason that helps me is because negative 1 to the negative 2 power is the same thing as negative 1, or excuse me, 1 over negative 1 to the positive 2 power. And of course, negative 1 squared is just 1, so this whole thing is equal to 1. So if this whole thing right here is equal to 1, then it shows that negative 1 to the n minus 1 is the same thing as negative 1 to the n plus 1. Okay, so I can go over here and just change that to a plus. Okay, and I'm going to clean this up on the inside, and I'm also going to take care of this. So I have the series, I move that 1 over, n equals 1 to infinity, with negative 1 to the n plus 1, times 1 over 3n, that's going to be a minus 3 plus 5, so plus 2 to the fifth. Okay, so we have it in the correct form. We have it in terms of n. If I want to find the nth partial sum with n equals 2, that will be the series from n equals 1 to 2 of negative 1 to the n plus 1 times 1 over 3n plus 2 to the fifth. Okay, so that will be two terms. One for n equals 1, one for n equals 2. We'll add them together. Okay, so the first one will be negative 1. If we plug in a 1, 1 plus 1 is 2, so 2 times 1 over 3 times 1 plus 2 to the fifth. That's the first term. Plus negative 1 to the, now we're plugging a 2. 2 plus 1 is 3, to the 3 power, times 1 over 3 times 2 plus 2 raised to the fifth. Okay, so let's see what that gives me. The negative 1 squared goes away. This becomes 5 on the inside here, so 1 over 5 to the 5 power And then the negative 1 to the 3 gives me, it stays negative. So I'll put a negative out front. And let's see, 6, 7, 8, 8 to the 5th. So minus 1 over 8 to the 5th. Okay. If you combine those together, you'll get 0.0002895. Okay, and we're rounding that to 7 decimal places. All right, so that's the nth partial sum with n equals 2 rounded to 7 decimal places. All right, and as we said earlier, now if we want to know how close is this to the real sum, if I were to actually take this thing and send it all the way to infinity and add up all the sums of this alternating series, how close is this to the actual answer? Well, this theorem that we have says that if I just take the very next term, it'll tell me how close I am to the actual answer. Now, that's just a margin for error. It doesn't mean that's the exact amount of error that I have, but it's saying there's no more error than the next term. So the next term is just going to be plugging in a 3, because we already did 1 and 2. So if I plug in a 3 into this, okay, in just the term, not the sum, just the term. So I'll plug in a 3, I get negative 1 to the 3 plus 1 times 1 over 3 times 3 plus 2 to the 5th. Okay, this, it gets raised to the 4th power, right? So it just goes away. Negative 1 to the 4th is just 1. So this becomes 1 over, let's see, this is 9 plus 2 is 11, 1 over 11 to the 5th. So our maximum error of this answer is 1 over 11 to the 5th. And if you work that out and put it and round it to 7 decimal places, that's going to be equal to 0.0000062. So that tells us that if we only use n equals 2, we only do 2 terms, then this is within this much error of the actual answer if we used infinite terms. Okay, so that means it's really close. This is really close to what the answer would be if we used, we kept going and used infinite terms. It's this close to the answer, within that close to the answer. And that's your error.